Hello, friends. Today we are going to uh, discuss the Eisenstein's criterion to find irreducible polynomials. And Eisenstein's criterion gives sufficient conditions for the existence of irreducible polynomials. So let us start. So it says that let D be a unique factorization domain, and E the quotient field of D, quotient field of D, and fx a polynomial is given by a naught plus a 1x plus a 2x square plus to a n minus 1 x n minus 1 plus a n x n non-constant non-constant polynomial in dx. Now suppose that there exists a prime p in the unifactorization domain D such that number one, the prime p divides a naught, a1, a2 up to a n minus 1. So p divides ai for I equal to 0, 1, 2 up to n minus 1. Number 2, p does not divide a n. P does not divide a n. And number 3, p square of the prime p does not divide a naught. Then the conclusion is that fx is irreducible in ex. Moreover, if the polynomial fx is primitive, then it is, that is, f is irreducible in dx. So if we can find, suppose that this polynomial is given, and if we can find a prime p which satisfies these three conditions, I repeat once again, p divides ai for I equal to 0, 1 to up to n minus 1, that is p divides a naught, a1, a2 up to a n minus 1. P does not divide a n, this one, and p squared does not divide a naught. then the conclusion is that the polynomial fx is irreducible in in ex, where e is the quotient field of the unique factorization domain D. And moreover, if the polynomial is found to be primitive, then fx will be an irreducible polynomial in dx. Now, in particular, if we take here z, the ring of all integers, you know that this is a unifactorization domain, and its quotient field is the set of all rational numbers, quotient field of z. Now we take a polynomial fx. This is a non-constant polynomial in the ring zx, and suppose that there is a prime integer p in z, such that p divides, the conditions are same as it in the case of general, and the conclusion will be over here, is that fx will be irreducible in qx. Moreover, if fx is a primitive polynomial, then fx will be irreducible in zx. Now we take an example. So we consider here the infiltration domain as the set of the ring of all integers, and q the quotient field of z, and we take fx as 5x to the power 4 plus 4x cube minus 6x square minus 14x plus 2, and this polynomial is in zx. We can consider this one. Now we see that this one is 4, 6, 14, 2, and each of these numbers is divisible by 2. So we take the prime p as 2 over here for this polynomial at least, and then let us check those three conditions. Then number 1, 2 divides 2 divides minus 14, 2 divides minus 6, 2 divides 4. So 2 divides 2, 2 divides minus 14, 2 divides minus 6, 2 divides 4. Here this one is a naught, a1 is minus 14, a2 is minus 6, a3 is 4, a5 is 5. Number 2, we have to check p, that means 2 does not divide this one, so coefficient 5, so 2 does not divide 5. And number 3 is 2 square, so p square, so it will be 2 square, it is 4, and 4 does not divide this constant term, so it is 2. So we see that if we take the prime as 2, then it satisfies all the three conditions of the Eisenstein's criterion. So the conclusion is that the polynomial fx is irreducible in qx. Now we check whether this polynomial is uh, primitive. So for we have to find the content of this polynomial, and we know that content of f, it is denoted by c of f, is GCD of all the coefficients, that is 2, minus 14, minus 6, 4 and 5. So GCD of 2, minus 14, minus 6, and this one 4, and this one 5. So it will be 1, and 1 is a unit, is a unit. And so the conclusion is that f is primitive polynomial, and hence by Eisenstein's criterion we say that this polynomial fx is irreducible in zx, or you can say that this polynomial is irreducible over z. Here too we can say that fx is irreducible over q.